Welcome back to an introduction to real analysis. We're now in chapter 6, section 1, pointwise and uniform convergence of sequences of functions. So until now, when we talked about limits of sequences, we always talked about sequences of numbers, but a useful concept is to consider instead a sequence of functions. So for example, a solution to a differential equation might be found by finding approximate solutions, and then the actual solution is some sort of limit of the approximations as the approximations get better and better. When talking about sequences of functions, what's a little difficult and tricky is that there are different notions of what this limit might mean. So we're going to describe two common notions of a limit of a sequence of functions. So here is our first definition. Let fn be a function from a set S into the real numbers for each natural number n. Then we say the sequence of functions fn converges pointwise to a function f if for every point in S, the limit of fn of x converges to f of x. So what does this really mean? Well, limits of sequences are unique. This was proposition 2.1.6. If a sequence converges to a number, it can only converge to one number. I'm not going to bother reflashing that on the screen. So if a sequence of functions converges pointwise, its limit is unique because at every point in the domain, this limit can be at most one number, meaning this is properly a function. Now it's common to say that fn converges pointwise to f on some subset T if the convergence holds for all points in the subset, meaning the sequence of functions fn restricted to T converges pointwise. Let's look at an example specifically. Let S be the interval from -1 to 1, and fn of x is x to the 2n. Now, for each x other than plus or minus 1, the absolute value of x is less than 1, and therefore the absolute value of x squared is less than 1. So if I start raising this to the nth power, we've established previously that if the absolute value of a real number is less than 1, then when you raise it to the nth power and take the limit, this goes to 0. So for every x except the endpoints, the limit of the fn of x is 0. But at x equals plus or minus 1, x squared is 1, and therefore when I begin raising this to the nth power, we have the constant sequence 1. So the sequence of functions fn converges pointwise to the following function. It is 1 at the endpoints and 0 everywhere in between. Another example, pointwise convergence is quite useful when discussing series. Consider, for example, the power series given just by powers of x, and take this to be a limit of fn of x, where fn of x is the partial sum, which is simply a degree n polynomial. Now we saw back when we were discussing power series, this converges pointwise to the function 1 over 1 minus x. Okay, so if we take the pointwise limit of these partial sums, we get 1 over 1 minus x. But the fn are in fact polynomials whose domain is all of the real numbers, but this limit only holds pointwise for x between plus or minus 1. So in this example, when we state that 1 over 1 minus x is equal to this power series, we really implicitly mean only between plus or minus 1, not on all real numbers where the individual polynomials are defined. Another example, let fn of x be the sine of n times x. Fn of x does not converge pointwise on any interval. There are isolated values, for example, x equals 0 or pi, where the sequence converges, it's constantly 0. However, it is an exercise to show that in any interval, there will be points for which the sequence fn of x does not converge. Here's a picture of what the graphs of sine of nx look like. As n gets larger, the graph is drawn with slightly lighter shade. Essentially, as n gets higher, you're increasing the frequency of this curve. So as n is small, we have a low frequency wave. As n gets higher, we have a higher frequency wave. If you pick any particular x and look at what is the value of the sine of nx, you get this, this, it bounces around a lot as n increases. That's essentially what you need to prove in the exercise to establish this example, that for any interval there will be values of x where the sine of nx does not converge to anything. Now, before we move on to this second notion of uniform convergence, we're going to reformulate pointwise convergence in a marginally different way. We're going to leave the proof of the following proposition as an exercise. And here is said proposition. Let fn be a sequence of functions mapping s into the real numbers and f be another such function. Then the sequence fn converges pointwise to f if and only if, for every x in the set S, for every epsilon which is positive, there exists a natural number capital N, so that for any natural number little n, if it's bigger than or equal to capital N, then the distance between f little n of x and f of x is less than epsilon. As we discussed, we're not going to prove this here. It's really just applying what it means by definition for a sequence of real numbers to converge. This was one of our earliest definitions back in chapter 2. The key point is that the capital N that you have to show exists is allowed to depend on both x and epsilon. So for every x, for every epsilon, you can pick a different n. If you pick epsilon, and then you let x change, you might be changing which capital N exists. Similar to the distinction between continuity of a function on a set and uniform continuity on a set, if we could pick one n that held for all x, we would now be defining what's called uniform convergence. If you can pick this n to only depend on epsilon and not rely on x, you can move around these quantifiers. And that's how we're going to define uniform convergence. So here's the definition. Let fn be a sequence of functions mapping s into R and f be another such function. We say that the sequence of functions fn converges to f uniformly if, for every positive epsilon, there exists a natural number capital N, so that for every x in S and every natural number little n, if little n is bigger than or equal to capital N, then the distance between fn of x and f of x is less than epsilon. Now in uniform convergence, our choice of capital N has to be made based only on epsilon, but not on little x. So we need to find a capital N as some sort of cut-off index so that the desired inequality at the end of the definition holds at every point x. So here is a sort of picture. We want to have our function f of x and then specify a distance epsilon so that every f little n is in this tube at every x, as long as the index n is big enough. So uniform convergence is a stronger condition. It will automatically imply pointwise convergence. To prove this, it's just a quick application of proposition 6.1.5, which was our proposition sort of formalizing the notion of pointwise convergence. The real key is just, if you assume uniform convergence, then for every epsilon, there is an n that works for all x. So for every x, let epsilon be positive, pick the n that works everywhere, then it will work for this particular x. This is very similar to way back when we proved that if a function is uniformly continuous on a set, then it is continuous on the set. Okay, so now let's state this as a theorem. We're not going to formally write out the proof. So proposition 6.1.7, consider a sequence of functions fn mapping s into the real numbers and f another such function. If the sequence of functions converges to f uniformly, then it converges to f pointwise. In other words, uniform convergence is stronger than pointwise convergence. Now, the converse of that previous proposition is not true. In other words, if all you know is that you have pointwise convergence, that does not immediately imply uniform convergence. Consider the sequence given before. Fn maps -1 to 1 by taking x to the 2n. We've already seen that we have pointwise convergence to this function, which is 1 at the endpoints and 0 everywhere in between. Now let's pick epsilon equal to 1/2. If we presumed that the convergence was uniform, then if we took little n to be big enough, this function would be within epsilon of this everywhere. Now, since epsilon is 1/2, to be within epsilon of 0 is to say that the value is less than 1/2. Notice that this function is never negative, so that's automatic. So we would be saying everywhere between plus or minus 1, fn of x is less than 1/2. So now what we have is we have f sub n is always less than a half until suddenly at the endpoints it is equal to 1. However, f sub n is a continuous function, so you can't skip values like this. This would violate the intermediate value theorem. So this convergence cannot be uniform. If, however, we take the same sequence of functions, but we only consider the interval from minus a to a, where a is less than 1, then convergence is uniform. A to the 2n goes to 0 because the absolute value of a is less than 1. So just considering x equals a, for any positive epsilon, there is a cutoff index capital N, so that past that point, the absolute value of a to the 2n is less than epsilon. However, for every x in between plus or minus a, the absolute value of x will be less than or equal to the absolute value of a, in which case the absolute value of x to the 2n will be less than epsilon. And this now holds at every x, so we have uniform convergence. So here's another very slightly modified version of convergence. For bounded functions, we can assign a certain non-negative number, which measures how far away the function is from the constant function 0. Then we can say that the distance between two functions is the distance of their difference to 0. Then we translate a statement about uniform convergence into a statement about this distance of functions to each other. And we're going to formalize all of this quite shortly. So definition 6.1.9, suppose you have a bounded function on a set S. We define, this is called the norm of f, or the S norm of f, to be the supremum of the absolute value of f of x on the set S. So across the set, take the absolute value of the function and take the sup of that. Having assumed that the function is bounded is to assume that this supremum is a finite number. We call this the uniform norm. There are some variants in wordage to refer to this. In this textbook, it's called the uniform norm. It is more often referred to as either the sup norm or the L infinity norm. And also, more common notation is not to put the subscript being the set, but to use subscript u for uniform or sup norm, but really the most common way you see this is with a subscript infinity in reference to the L infinity norm. Now, one benefit to the notation adopted in this text is that the subscript denotes the set over which the supremum is taken. So if you want to refer to a subset of Sk, and you simply put the k norm of f in this notation here, it's clear from this definition that you're now taking the supremum over the set k rather than over the set f. But I should mention that in other textbooks about real analysis, in my experience, by far the more common notation is this, the L infinity norm. Often that notation with a subscript infinity is used while referring to it as the sup norm, but the written notation almost always is that subscript infinity. In this book, however, we're not going to talk about any other norms. So since this is really the only function norm we're going to work with, there's no opportunity for confusion. Proposition 6.1.10. A sequence of bounded functions fn, mapping s into the real numbers, converges uniformly to some f if and only if the limit as n goes to infinity of the s norm of the difference fn minus f is 0. Well, we'd better prove it. So let's recall all of the relevant definitions. Here they are. We need to talk about uniform convergence, also this norm. Let's assume first that the limit of the s norms of fn minus f is 0. We now want to prove uniform convergence to f. So let epsilon be positive, we need to find some capital N. However, we have assumed that this sequence of norms converges to 0. So since we now have a positive epsilon and we have a sequence converging to 0, there is a capital N, so that for all little n past that point, the s norm of fn minus f is less than epsilon. But what's the definition of that norm? The supremum of the absolute value of that difference. Meaning, if the supremum of the absolute value is less than epsilon, then for every x, that absolute value is less than epsilon. And that's exactly what we would need to establish to get uniform convergence. Here it is. So that was fairly straightforward. Let's look at the other direction. Let's assume that Fn is converging to F uniformly. We now want to prove that the sequence of S norms converges to 0. So now we're just trying to show that a sequence converges to 0. So let epsilon be positive. We need to find some cutoff index related to this sequence, but from uniform convergence, we do get a cutoff index capital N. So for all little n past that point and all x in the set, we end up with this absolute value being less than epsilon over 2. This is going to be a minor convenience. If the absolute value of fn of x minus f of x is always less than epsilon over 2, we can take a supremum over all x's and get less than or equal to epsilon over 2, which is less than epsilon. If the supremum of this absolute value is less than epsilon, then the S norm is less than epsilon, and the proof is complete. And now yet another comment on terminology. So sometimes you will come across people saying that the sequence converges to F in the uniform norm or converges to F in the sup norm instead of what we're calling converges uniformly. There are reasons for these minor changes. They're ultimately unimportant for us. The previous proposition shows that in the context of bounded functions, the two notions are completely equivalent anyway. So let's look at example 6.1.11. Let Fn be defined on the interval from 0 to 1, be given by x plus the sine of nx squared, all divided by n. Then this sequence of functions converges uniformly to simply f of x equals x. And the proof is not very difficult. Let's take a look at this sup norm of the difference of Fn to what we are proposing it converges uniformly to. Well, if I subtract this x, I'm merely left with the sine of nx squared over n. The absolute value of that difference, in other words, the absolute value of sine of nx squared all divided by n, well, this numerator is the sine of something. In absolute value, it's no bigger than 1. So this absolute value, the supremum, is definitely less than or equal to 1 over n, and I can certainly make that go to 0. So as n goes to infinity, the limit of these S norms is 0, so by the previous proposition, we have uniform convergence. Now, using the uniform norm, we're going to define Cauchy sequences of functions in a similar way as we defined Cauchy sequences of real numbers. So definition 6.1.12. Let Fn be a sequence of functions. They're all bounded. They map the set S into the real numbers. We say that the sequence is Cauchy in the uniform norm, or just uniformly Cauchy, if for all positive epsilons there is an index capital N, so that for any two indices, little m and k, if they're both bigger than or equal to capital N, then the S norm of the difference Fm minus Fk is less than epsilon. Here's prop 6.1.13. Again, let Fn be bounded functions mapping the set S into the real numbers. Then the sequence of functions is uniformly Cauchy if and only if there is a function f such that the sequence of functions Fn converges uniformly to f. In other words, uniformly Cauchy sequences converge uniformly to a function, if and only if. Okay, we've got to prove it, of course. Let's throw all these definitions back up here that we need. Let's suppose we have a sequence of functions and we'll assume it's uniformly Cauchy. So this down here, 6.1.12, holds. Now we need to show that there is a function that it can be proposed to converge uniformly to. So first we claim that for each x, the sequence Fn of x is a Cauchy sequence. So to prove a sequence is Cauchy, let epsilon be positive, and then find a cutoff index past which you get a useful inequality. Now, since the sequence of functions was assumed to be uniformly Cauchy, that assumption gives us that there is an n past which this sup norm is small. But that's a supremum over all x, meaning certainly for the x we chose, Fm of x minus Fk of x is less than epsilon. In other words, the sequence Fn of x is a Cauchy sequence. So for every x, the sequence Fn of x is Cauchy. Therefore, that sequence converges. So we can define f of x to be the limit of Fn of x. In other words, we can properly define a pointwise limit of the sequence Fn because the Fn's form a Cauchy sequence of points they have a limit for every x. Now what we want to show, however, is that the convergence on the scale of functions, not just at a single point, but the functional convergence is in fact uniform. So now we can propose this definition here, that the convergence to f is uniform. So let epsilon be positive. From our assumption that the sequence of functions is uniformly Cauchy, there is an n, so that for all m and k past that point, we have this sup norm less than epsilon over 2. So we have a pointwise limit f of x, but we also have that for large enough indices, this sup norm is less than epsilon over 2. Therefore, fm of x minus fk of x is less than epsilon over 2. We can now just take a limit as k goes to infinity, fix m to be anything past the cutoff index n that came from this sequence being uniformly Cauchy. Let k go to infinity. Now we have a pointwise limit here, and we conclude that fm of x minus f of x is less than or equal to epsilon over 2, which is certainly less than epsilon. So we have achieved what we wanted here. So we've got uniform convergence of the fn's to f. Now we have to go the other way. Let's suppose that the fn's do converge uniformly to some f. So this is now our given, definition 6.1.6. Now we need to establish that the sequence of functions is uniformly Cauchy. So let epsilon be positive. Now we need to find a cutoff index n, but we've assumed definition 6.1.6. So having said let epsilon be positive, there is some capital N so that the rest of this holds. Fn of x minus f of x is less than any arbitrary positive amount. We're going to use epsilon over 3. And this holds for all x. Therefore, for any two indices past capital N, fm of x minus fk of x, well, I throw in this plus or minus f of x and use the triangle inequality. But now I have two indices, both past the point where uniform convergence to f of x gives us this is less than epsilon over 3 and this is less than epsilon over 3. So overall, fm of x minus fk of x is always less than 2 epsilon over 3. I can now take a supremum over all x in the domain S and get that the sup norm of fm minus fk is no larger than 2/3 epsilon, which is definitely less than epsilon, and we have shown that the sequence is uniformly Cauchy. So what did we discuss? Given a sequence of functions defined on some set S and some other function f, if at every point x you get convergence of fn of x to f of x, that's called pointwise convergence. It's the base level convergence of a sequence of functions to some other function. Now what follows is that the absolute value of fn of x minus f of x goes to 0 for every x. That does not itself imply that the supremum of the absolute value of fn of x minus f of x is small or converges to 0 or converges to anything. A stronger notion of convergence is uniform convergence, which does handle this supremum here, thanks to various equivalent definitions that we threw about and the propositions. Okay, I also want to point out that one of our examples was highly illustrative, this x to the 2n. Every x to the 2n is continuous, but on the interval -1 to +1, it converged pointwise to a function that was not. We also saw that that sequence of functions was converging pointwise and not uniformly. That's a big segue into the next section.